What this is this. So this is if you've been in a lot of my other classes, I do this with my other classes. Generally, don't do it for this one, but so this is recording what I'm saying right now. What it does is everything that I write on the board, right on this whiteboard, it automatically you can watch it again on YouTube. My voice is ridiculously squeaky online. I don't know why. It's something to do. Okay. I hate the way my voice sounds. But I have a cold, so I have a slightly deeper voice, so it's not too bad. I blame my son. So, what were you guys supposed to do last time? What is it? What is the survey about? Okay, so is gender something that is objective, empirically measurable, or is it something that is a concept? Okay, a concept. So what's a problem with a concept in psychology? What do you have to do for a concept? Say it again. Okay, how do I make a concept empirical? But so I name number them 1 and 7. Go. To help me understand the concept. So this is something this is what we tried to do last week. Come on, box. Oh, I didn't make it. It'll automatically box and circle things, which is really cool. Anyway, so when you take something that is a concept, you have to do something called parameterize it. Well, yeah, because when you have a concept, you have to turn it into a measurable parameter. Thora was talking to me in the office about her possible final project. And she goes, oh, I want to look at kids and playing video games and bad attention. Okay, can we measure whether the kids play video games or not? Yes. We can understand that question. Then we can ask the simple question of, we can measure attention. I can give a reaction time test to kids and measure their attention by shifting attention. We'll be able to do that with us in the next week or so, 2 weeks. But what's a problem when you try to parameterize something like kids and attention? Okay, what do you mean by large parameters? What does that mean in your head in non? It's the right. Okay, but this is not. Okay, so we have to do something that operate. I'll get this. I can't say it, but I can spell it. You need some sort of operational, what's called operationalization. Said it. Operationalization. When you operationalize something, you are defining it based on its measurement. This is really important for this class. When you are trying to measure anything, you have to operationalize it. You have to define it by a measurement. Okay, this is super tricky because, so how do we parameterize attention? What's the first thing you have to do? I just wrote it down. Someone try and say it. It's hard to say. Operationalization. Empirical operationalization. The problem with the parameter of attention. The problem with the parameterization of attention is that the number that you get is hard to define. It's hard to define what is attention, what is not attention. So why did you use the term standard deviation? She didn't really use the word standard deviation, but that's what she meant when she went like this. What defines a parameter? What defines the boundaries of a parameter? Excellent. The mean is the first place to start looking. for a parameter. In stats, we call it x bar because it sounds cooler than mean. What defines the standard deviation defines how spread out it is. Okay? In non-stats terms, we talk about the range of scores. Range of scores makes sense in psychology. Standard deviation makes sense to about a third of you, maybe less. Okay. I missed. All right, it's close. This is a parameter. This is a concept. When you parameterize something and you have empirical, observational, operational definitions for things, you can calculate a mean. The mean has a predictable range. The range is called the standard deviation. Good morning. Okay, so what falls between -1 and +1 standard deviations in your parameter? It's like 40%, but more. Come on, 34 and 34. Get the memorizing tables out. Okay, sorry. I don't expect you to remember that. Okay. 68%. Yeah, then it goes to 95. Then it goes, okay. So, 97. Anyway, but stuff like that. I use 1.96 is what we use in psychology. Just say, yeah. Okay, so this range right here is what we call normal. It's what we call normal. Okay? So when we have something that is considered normal, we can say that it is parameterized. It's parameterized. So how do I know if you have bad attention? Sorry, I'm about 4, so what? Just kidding. Okay, so once I empirically operationalize the behavior that I'm trying to measure, then I compare it to the average people. I compare it to the average person. And then I compare it. So what is the standard deviation? I'm sorry for doing stats, but that's very confident. Come on, someone knows standard deviation without looking at Facebook. She's on Facebook. Okay. I can see the monitor behind. She's not listening. It's on Facebook. Okay. So standard deviation is the sum of x minus the mean squared divided by n. Obviously, we all remember that. No, we are using population, so right now we're using n. We'll talk about degrees of freedom in a few minutes, so then it gets exciting. Okay. All right. So, anybody remember what standard deviation means in real people language? That's 68%. That's exactly what you just said. So what it means is it's the average, when you add something up and divide by n, it's the average amount each person is not the mean. Okay, so when you have a standard deviation, I don't expect you to really embrace the wonderfulness of standard deviation. So Francis Galton used it to become a racist. It was awesome. Anyway, but the standard deviation is the average amount that each person is not the mean. If you have data that is weird or wonky, we're going to talk about weird and wonky data today. Okay, that's one of the main points what we're talking about today. You have very high standard deviations. If you have very high standard deviations, anybody remember what the stats term's called? Why lots of very high standard deviations on a distribution? No one remembers. It's called plateau curtain. Yeah, plateau curtain. It's called kurtosis. Kurtosis is the squishiness or fatness of the distribution. Or, and it's a plateau-kurtic, the distribution looks like this. Here's my mean, here's my parameter, the distribution looks like this. I missed. Oh, look, it triangled it. Wait, there we go. Cool, it took a part of the x with it. Excellent. Okay, that's not messy at all. Boy, if you got a distribution like that, you should play the lottery. Wait, it's a cohander. Okay. Wait for it. There we go. Okay. Okay, so if I have my distribution that looks like that, and there's my little x again. Okay, if I have a distribution like this, what does this tell me about how spread out the scores are? Well, I just committed some statistics, assume aside. What does this graph represent? No. What is this? If I'm showing you this graph, and I'll talk about this graph sadly too much today, what does this graph mean? What is it showing? No. Go back and simpler than that. What is a graph above? I'm trying to use this monitor. Okay, what does this graph above show? Okay, so we have to go back to even more simple basic. What is the x-axis of this graph? X, the x of this graph is x, which is your score. What is the y value of this graph? This is why I have to do this. Well, what is mode? That's actually correct-ish. Oh, so close. How do you know a particular score is the mode? What do you count? But how high it is mean? There you go. The y-axis is frequency, number of people. It's called a frequency histogram. Why is that important to know? Well, you never, ever see these when you're looking at data, when you're looking at research projects. You never, ever see these. But this is hugely important for us because it helps us define what our parameter is. So if I have a normal distribution like this, the highest frequency score is the mean. That's what makes the distribution normal, where the mode and the mean are the same. That helps. There's one other score, though. See, I just forget. I just assume that people know this, and I just motor on, and I realize, stop, back up. All right. So the mode is the, what's the mode? Oh, come on, people. You got to make noise, otherwise this gets really boring. I'll just start coloring. Yeah, it's the highest frequency score. Okay, we'll talk about what is the median. The middle score, 50% N, below 50% N. Why am I underlining N above? Does that have anything to do with the value of the score, or is it just the number of scores? Just the number of scores. When you hear median, they just talked about median home prices in San Diego, that the median home prices are changing in San Diego again. Okay? The median means that 50% of the houses sold are above that amount, and 50% of the houses below are sold are below that amount. So it doesn't tell me about how much the average house costs. It just tells me where your house sits in the sorted range of houses. Whenever you have a distribution that looks like this, San Diego home prices look like this. There's a house in Fallbrook, what's actually not part of San Diego. I don't know, is Fallbrook part of San Diego officially? Yeah, it is. Yeah. So there's a house in Fallbrook designed by this really fancy architect that sold for like $40 billion or something stupid. It looks like a giant wing on the top of a hill. And I forget it sold for a couple billion. How does that stack up to our house worth about 700,000? Bought it for 2. Oh yeah. Sorry. We could barely afford it when we bought it for 2. We could not afford to buy it now. Okay, but how does it stack up? If I add an 2 billion into the average home price, what happens to everybody's home value? Okay, so so this is the spread of it is it's called your kurtosis. That's how spread out it is. That means it has a very high range. A skew means that the mean is shifted. Okay, so if I were to take a normal distribution, like this, a very spread out normal distribution, and then I add one score, way the heck over here, $2 billion. Okay, I had a really wonderful student named Travis Lee. I use this example in my stats course all the time. Travis was a baseball player at San Diego State. This is back in 1996, 5 or 6, somewhere in there. And he was a sophomore in the sophomore on the baseball team. He's taking my introduction to psych course. He's sitting there pretty much cheating off the soccer girl the entire class, not caring, baseball hat down. Why is he in class? So he can play baseball. He has to pass his classes, otherwise he can't play baseball. Anyway, Travis is hilarious. Disappeared halfway through the semester. Gone. And we're like, and then I hear the news. Travis Lee, San Diego State pitcher, signed for the Arizona Diamondbacks. $14 million signing bonus. Why did he abandon ship on college? $14 million sitting through a boring psych class that I don't care about. I might even leave for $14 million. Okay, and so what happened to the average amount of money that each student had? Everybody got a giant pay raise in the class because the average amount of money that each student had went up a tremendous amount. The average amount of money that each student had in class after Travis got the $14 million signing bonus was almost $300,000. Did everybody really have $300,000? No. It would be nice if we were socialists, that's how it worked, but we're not. Yeah. But what happened is that why did the average go up? How do you calculate the average? It's the sum of the scores. So you add up all the dollars in everybody's pockets, and then you divvy them out amongst equally to everybody. The standard deviation is the amount, the difference between each person gets. So are some people going to be, like, would Travis be really pissed if we socialized the class and just put his money into the group and then spread it out? Yeah, because is he way different than the mean? Yeah, because he has such a high standard deviation away from the mean, he is going to lose a lot of money. Well, okay, we'll get to outliers in a little bit. But whenever you collect data, you have to make sure, going back, that you are focusing on you're trying to parameterize a concept. When you parameterize the concept, then you can figure out what is the expected mean for this distribution. What is my expected population? That's why you need to go out and somebody else's research and steal their ideas. Because have they tested it already? Yes, and if they've tested it already, they've already not done the ones that don't work. Whenever you come up with a great idea that sounds really awesome, and you keep Googling it and you can't find anything, it's probably because there's nothing there. What was the one that Michaela did? I had a student, Michaela, she did a really, she goes, there has to be something. I just know there is. Oh, tall people are more extroverted. That's what it was. Well, she couldn't find any research about height and personality. So do you think that tall people are more extroverted? No. Did she find tall people are more extroverted? No. She did, however, that tall people tend to go to the front of things, which I thought was pretty funny. Why do tall people tend to go to the front of things? You'd think that would be the opposite. So that asks a really interesting question. Wow, are tall people more pushy? When standing in a crowd, I like to be closer to the front. And tall people said, yes. More likely. Wasn't what her primary hypothesis was, but she found that. So then maybe that could lead to another experiment. Maybe short people don't like to be in front because everybody notices they're short. Huh. I don't know. I always take up a lot of space, and I always feel bad about blocking space, so I always go to the back. But, so the idea that when you try to parameterize something, you're trying to define it based on a measurement. The measurement has to be normally distributed. If a parameter is normally distributed, then we can make predictions using it. So this is the hardest part. I keep saying this all semester. The hardest part is right here. Like I was using your example with the kids and attention with their phones. Okay? And so what is the average reaction time? How would we find the average reaction time? Well, but wait, how do I measure reaction time? Before we can get to the many people, before we can get to the subjects, we have to parameterize and operantly define attention. So before we can even ask any questions, how do we find out what the normal reaction time is? Yeah. I hate this term. This has become an actual real word now. Search it up. Learning Resource Center. We also call it the library, but I always spell library wrong, so I write LRC. It's a defense mechanism to deal with my incompetence. Now, so you search it up. So it's funny because does it make sense to look it up or search it up? And my generation used to look it up. Because it was like a book, weirdness, pages, turning, card catalog. What? Okay, what? But then you have to, so now kids search it up. For a long time, we just said, well, Google it. But then the young people just say, I search it up. And now I hear people saying search it up on the radio. Once it gets to radio, it's mainstream language, and people use it more than anything else. Okay, so you start looking for other people's research about what the average reaction time is. And then once you find other people's research, we use this little term. It's a mu. This little term is called a mu. You're going to be very tired of these in a little bit. I'm sorry. A mu is a population. Yep. It's a population mean. Or a... Whoa, that was weird. Triangle no? Oh. Uh-oh. Whenever you find a mu, it's a population mean, what we call a known parameter. We found a really interesting thing in my statistics class that people who drink milk are taller than people who don't. And then this semester we found people who eat breakfast every day and drink more than 3 and 4 glasses of milk a day are not only taller, but they weigh the same. That's a lot, as everybody else who doesn't what I just said. If you eat breakfast every day and you drink 3 to 4 glasses of milk a day, you are taller and thinner than everybody else. Well, actually, you're not really, well, you're thinner because you're taller but weigh the same weight. So we happen to have the Center for Disease Control data. We have 1 million subjects in the data. Rachel, quit it. It's distracting me. Rachel. Okay, so if we have population parameter data, we can make known conclusions. Could we test that hypothesis in my introduction to psych students?
No, because it would be not a
Okay, so yeah. We happen to have a problem. We happen to have a problem of samples. This is where we get into, if we know population parameters, if we have known things that work, that are very consistent. Attention is a very predictable, consistent thing. We can measure attention extremely predictably, extremely consistently, because we can do reaction time programs. It's very easy, it's very simple, and we can do this. We did this with my son's class last year. Measured it's called the Stroop effect. It's measuring attention and paying attention to colors versus words. Okay? But we have a problem with sample. If you have a biased sample, what happens to your distribution? Could be skewed based on the biased sample. Okay? Anybody know the big problem at Cuyamaca with our bias? But why does that affect us? Aside from cultural and ethnic diversity benefiting anything else. But aside from that. Okay, wait. What else? Listen. What's another problem with Cuyamaca College campus? We use Latinx because a lot of them are actually from Mexico. Yeah. Okay, so but 50% of our students are, over 50% of our students are Latinx and people from identified Middle Eastern. Middle Eastern could be considered anything from Chaldean to Muslim to Iraqi to Syrian to Afghani. So we just label it all as Middle Eastern. Here you go. Asia. Anyway, so because of our sample bias, can we compare ourselves to a known population? Okay, so then we can compare it, but our sample is going to be skewed. What's a skew mean? I put it up here. The mean. So Hispanic, Latino, Latinx folks, how do they stack up and height-wise compared to non-Latinx folks? They're shorter. Turns out, everybody who lives near the equator are shorter. As you get further away from the equator, what happens? It gets cold. Let's see, what happens to milk when it's warm? Spoils very quickly. If you live in, anybody know the tallest country in Europe? It used to be Dutch, but it's not anymore. Alps, yeah, somewhere in the Alps. The tallest people in the world are people who live in the Alps, and then it's in the Dutch, and then it's up other northern Europeans like Finland and all those places. That's where all the tall people are. What are Dutch known for? Dairy. Dairy. A lot in Pennsylvania. That's where the Dutch came. Actually, they're Germans. Don't call them that, though, because they changed them to Pennsylvania Dutch, because it used to be Germantown, and they changed it to Pennsylvania Dutch during World War II so that they didn't get picked on. Oh, World War I, sorry. Sorry, not important. Okay. But the problem is that our population is skewed to more equatorial folks, which are shorter. It doesn't work going south, though. It only works going north. People in South Africa, same height as people equatorial. Venezuela, same height as equatorial. I blame the Spaniards. Moving on. Okay. So this is our biggest problem for us to deal with this semester. This is our biggest problem to deal with this semester. You can have some really good ideas, but your sample frames will suck. What if you just dump it out? I'm going to write the word sample frame. What if you dump it out on Facebook or social media? Yeah. And do you hang out with your people? Yes. Well, no, not literally hang out, but it's really weird how our culture stratifies itself. We're doing this big equity training for our department right now, and it's fun because I teach this in my intro class, but it's fun to see it from the other disciplines' perspectives. But it's basically that when you get together with large groups of people, if you look at the racial makeup of your groups, what are they? For most people. Homogeneity. Operationalize homogeneity. That's it. Okay. So. Because in military, what do? They throw everybody together. But you develop a military culture. And the military culture is much different than reality culture for a lot of people. I have a lot of my former students that have been in the Army. They get out and they're like, I'm not in the Army. And it's hard to adapt because of the culture shift is so hard. Navy as well, but okay. So I'm going to zoom back out again and start thinking about big picture. What are some other things aside from sample bias? Oh, one more thing. I forgot about one more thing for sample bias. I meant to get into it. One more thing about sample bias. It's called your degrees of freedom. This is really important when we get into the next part. And you really have to pay attention to this. Degrees of freedom mean n minus 1. In other words, it's the amount of scores that are free to vary. So your degrees of freedom, n minus 1, are the amount of scores that are free to vary. This sounds kind of stupid. Thank you. But there are two different types of degrees of freedom that you have to pay attention to as a scientist. There's two really important kinds. Between groups and within groups. No. Go there yet. We will get there. Okay. So there's two different types of degrees of freedom. So if I'm asking you, what is your biological sex? How many groups do we have? 3. 1, 2, 3. How many degrees of freedom of group do we have? Yeah. Degrees of freedom between groups is 2. Hello. Between groups is, well, degrees of freedom is always n minus 1. If I have 3 groups, 3 minus 1 is 2. Okay, so you want to try to keep your between groups degrees of freedom low. You want between groups low, and I'll explain why in just a second. Within groups is your capital N minus 1. So the way you do this is total subjects. Your total subjects minus 1. So you're within groups. In other words, within your groups, you want to have a total number of degrees of freedom that is high. High within groups degrees of freedom, low between groups degrees of freedom. The reason is, well, let's analyze this. What if you have 10 groups? 10 groups of people you're trying to compare. How many subjects would you need? Well, if you had one subject broken into 10 groups, ouch. So why do you say 15? Yeah, so it's not a magic number, it's on a t-table test. What adds, this is what we give us what's called statistical power. It has to do with the formula of sigma divided by the square root of n. So, I don't think we'll talk about in this class, but it's a standard error of the mean. And once you get groups of higher than 15, the table normalizes. Over 30, it's the same as a normal distribution table. It has a lot to do with that, but don't worry about it. Okay. I'll go a little feed on it. Okay, so if I had 10 groups, if I have 10 different groups of people that I wanted to look at, how many subjects, how many degrees of freedom within groups would I need? 15 per group. Yeah, do you need 15 subjects to make a good parameterization? When you get less than 15 subjects in a group, the bias and the skew increase more. With fewer degrees of freedom, bias and skew affect the data more, yeah. So it's one of those things that it requires lots and lots of stats to understand. But, I mean, in a real simple way, when you're looking at the difference between groups, there's a mathematical formula to calculate probability, right? So when you look at this formula to calculate probability, hold on. I was listening to Bob Dylan before. Times they are changing. Okay, sorry. So here's a t-test table. Okay? Just because you ask why, there's 50%, there's 97%, here we go. Okay? So this is a table to look at cumulative standard normal distribution of probability of a particular score. So if you're at 1.9z, there's 0.0287 people beyond that z-score. Probability, right? This is based on a normal distribution of an infinite number of subjects. This is a mathematical curve based on an infinite number of subjects. When you have a distribution that is, let's see if it's on here, the t-table. When you have a t-score, there's more z's. There we go. So this is a critical values using a t-distribution. It's a different mathematical population, using means as opposed to normal scores. Look it up until 15. If you have 1 degree of freedom, how far out does it have to be different? How many basic z-scores? 12. 12 z-scores away from the mean if you have 1 degree of freedom. In other words, 2 subjects. But then when you get to 15, it goes to 2.13, which is much closer than the actual percentage that we like to use. We use 1.96, which is the normal distribution's infinite. But notice what happens after 15. 2.13, 2.06. Look at the difference between 15 and 24. Doesn't change very much, does it? And then you go from 24 to 30, and it doesn't change much at all. So if you have at least 15, mathematically you're like, that's good enough. Is more better? Not really. I mean, 1.96 versus 2, 60 versus infinite, not that great. If you're going to find something that's really there, you'll find it with 15 subjects. If you find, how do I know something's really there? I haven't had to think that hard for a long time, so thank you for asking me that question. We get to do that later in the semester in stats, but I haven't brought that up in my head yet. So what do you have to do in your experiment to find differences? Oops. Okay. Mike, it looks like Mike Wazowski to me. Okay. I'm going to scroll back to the top. What do you have to do? Parameterize your data properly. If your data is properly parameterized, in other words, if you find a measure that is successful, it's like for Rachel, the project that I want you to kind of work on is you're going to characterize the people's responses as intrinsic or extrinsic. So what does intrinsic mean? Somebody remembers this from intro. You focus inwardly. So if I'm stressed, I focus on dealing with my stress. If someone who focuses extrinsically would, I'm stressed, I'm going to go hit something. Locus of control, yeah. Locus of control, it's the same thing. Different definitions. But locus of, so if the person is reflecting because they're overworked and stressed, that's an intrinsic way of dealing with it. If they go work out or drink, extrinsic way of dealing with it. If they look outside of themselves and try to solve the problem, that's extrinsic. If they're trying to do inner peace things, that's intrinsic. And what's cool is that those concepts have been parameterized. There are scales that you can look at your internal and external locus of control. So these people happen to have the data that she has. These people that happen to have, you guys scaled that one the first day of class. Remember that? You tried to rank the different behaviors as personal, exercise. I know it was still like 3 weeks ago. Okay, 4 weeks ago. 5 weeks ago? I'm grading week 4 in my developmental class, so that means it's week 5. Okay, got it. Okay. So, but once you have a concept parameterized, then you have an operationalization. She is operationalizing the definitions that these people are giving, coding, which is empirical. And after she reads about intrinsic and extrinsic motivation, will she be able to code them better? Yeah. Because you define intrinsic and extrinsic more specifically, then you can code it 1 or 2. If you only have 2 groups, is that good? She has 120 subjects. She can code it as 2 groups or maybe 3 groups. What's wrong with only having 2 groups? But you, so she's 100% correct. If you only whittle things down to 2 groups so you don't have to have a lot of subjects, what's going to happen? You're going to miss something. If you only whittle things down to 2 groups, if you whittle things down to 1 degree of freedom, is there a lot of variability between the groups? No. And that's a biggest problem is low equals good, and you're able to find things better with less subjects, but low is also bad because, I'm going to write this up here because this is something that's really important. That what you might find might not really be there. If you narrow things down too much, if you generalize too much, you lose the point of the research. You miss something. Another thing is really important. Confounding variables. The reason we ask lots of demographic questions, we ask a lot of demographic questions, is to try to reduce confounding variables. Okay? So confounding variables is anything that you didn't expect. Anything that you did not expect in your experiment. I just pulled up this PowerPoint here so I can remember to spell this correctly. Okay. So confounding variables, anything that you didn't expect in your experiment. So what's a common confound that would be for attention? Does playing with your phone a lot lower your attention span? Well, you can't answer the question. That's a hypothesis. Yes. Okay, that's not. Everybody does that. Okay. So anecdotally, you can say yes. But how do we? How do we empiricize it? What are you going to measure? No. That's not. How do we? We got to start back at the beginning. Whenever you start with an experiment, the first thing that you do is go back to the top of this thing and parameterize something. Who has better attention, males or females? Since gender was the first topic we were talking about today. Well, you say females, but how do you know? I have Dave. There's a problem with psychology. Is that if we study psych students, what do most psych students be like? Come out right for it. Female. So we have a lot more females than males in my experiments because most people that take psychology are more likely to be female. Our sample frame is biased toward female. Yeah.
How does studying psychology or get rid of that correlation with not causation?
We'll get there because with correlational designs we'll talk about in a little bit. Yeah, so we'll get there. But when you see the math, it's obvious. But anyway, anyway, so okay, so getting back, so we can, if we asked, are males better at attention than females? What does that do to my degrees of freedom in my hypothesis? If I've got males and females and non-binary, so my degrees of freedom is 2. I have a parameter measuring reaction time. I can measure reaction time. So we have enough students in here. 1, 2, 3, 4. Always miss some poor guys. 5 guys in here right now. Is that enough to create a sample? Darn. But we have enough females to create a sample? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have enough females to create a viable sample, but we only have a few males to create a sample. And so, but luckily I happen to have lots of data from previous semesters of experimenting doing this, so it's perfect. We can ask this question. But what was the other question that we asked? Does playing with your phone affect reaction time? So we'd have to ask questions. We'd have to come up with a survey. How often do you just check your phone? How often do you check your phone? We took my daughter's phone away for 5 minutes just as a little experiment. She almost died. Well, yeah, you don't respond to someone on Snapchat within a few minutes. They get very upset of you. Especially said boyfriend. I'm like, I'll text him and tell him not to hear that you got your phone taken away. Don't do that.
So when you're asking a question like, thinking like of maybe a scientist who always uses spelling, but maybe the way he uses spelling is more.
Okay, so you have to step out of the anecdotal evidence. You have to step out of your own personal experience, and that's the hardest part. You all say yes when I ask the question. You shouldn't say yes or no. What you should start to do is say, oh, how would I parameterize that? How would I turn this from an open-ended question that I can anecdotally answer based on my observations to a scientific experiment? Wait. So you have to take this apart and make it completely boring and completely not fun. Science. Because why do you have to make it completely boring and completely not fun? Yeah. And to remove confounding and what's called artifacts. Artifacts are like confounds. Artifacts are things that you screwed up. Okay? Yeah, it's you. The biggest problem with doing experiments is you. Yeah. And that's because, do you screw things up? Yes, because we're human. Now this is a little bit out there, but I want you to kind of do this, and we'll take a quick little bit of break. Okay? So, why do we conceptualize things? No, we do not operantly define things. I ask a question, you immediately search your entire database of your own personal experience and come up with an answer. Yeah, it's conceptual. When you parameterize things, you're understanding it. Yeah, or they're called heuristics. They're also called schemas. Yep, they're also called, when you said heuristic, you ruined that was like third on my list now, and I can't remember what the first one on my list was. Thanks a lot. Concept, use exemplars. And there's one more that's there, but I forget what it's called. Nice. Okay. Stupid hierarchy of memory. Goes with heuristic. Oh, algorithm. RITHM? Oh. Okay. Heuristics, schemas, exemplars, and algorithms. These are all cognitive psych mumbo jumbo that mean the same thing. Concept. So like, my favorite example for this is a little bit dangerous in this classroom, but I'll do it anyway. Yeah, it should make more sense. So this is an off-string yo-yo. Why do you think it's dangerous in a computer lab? Lots of breakable things. Okay? But all right, okay. All right, I got that mistake. So in order to do off-string yo-yo, what do you have to understand? Well, what's funny is that you don't really have to understand a lot of physics. You don't have to understand the physical formulas, and you don't have to understand all of the actual physics that's going on. But what do you have to do? Well, no, just having fun. I just spin it and let it spin around on the floor, because that's highly entertaining. Okay, got the knot off. Okay, but in order for you to learn how to do something, I mean, this is a terrible yo-yo, but my really good one broke for some reason, not sure why. Okay, so in order to do this properly, there's a lot of timing involved. But is the timing exactly the same every single time? No, it can't be, because I am not robot. I don't do robot things, except for, the cool dance move. But what happens is that you learn a concept. Your body moves to the position where it should be, and what do? Hold on, you fine-tune it afterwards. So we use the feedback circuit. So once you learn how to do something, this is like my father-in-law always says this with volleyball, because he's been a coach for 800 years. He goes, the game slows down the more you play. And the same thing with my son with basketball. The kids that are really good seem to know where everything is and everything's going on. Well, one kid's like focused on the ball. He has no idea that the guy's going around behind him because he's hypervigilant and focused on the ball. And then the other kid who's not paying attention catches the ball and puts it in. The poor kid that's guarding the first guy goes, well, I didn't see him. But if somebody, as soon as you've been playing for a while, as soon as you put your guard on somebody, you look at him with this eye. What are you looking at with this eye? Standard chameleon style. You look in different directions. What do? You're paying attention to the rest of the game, so you set that behavior on what's called motor program mode, autopilot. You're still reacting to that world, but you're also paying attention to the rest of the world. And what happens is it's the same thing with driving. My daughter's not the best driver right now, but she's 15 and 3/4, so she'll be driving very soon on her own. But when she gets in a situation where she pulled out in front of a car, she didn't know what to do. What are the two things you do when you pull out in front of somebody? Speed up or stop. She just kept rolling slowly forward, which is very, very exciting if you're the carpool. Do not make the joke of handing a candle to everybody in the back seat. Catholic humor. Moving on. So, my daughter did not think that was funny. Get your candle back there, folks? I forget what patron saint of driving is, but it's important. Okay, anyway, but the idea of, once you have the concept, once you have the heuristic, the schema, you stop paying attention. And what do you start to do? You're driving, the driving becomes irrelevant. We use automatic motor programming. And the automatic motor programming becomes almost irrelevant. My handwriting is getting better with the computer, sort of. Okay, it's still terrible, but it looks just like my handwriting on the board, which I've discovered is terrible and useless, but that's not important. But my fluidity in using the computer to teach with is getting significantly better since it was at the beginning of the semester when I started doing it. Yeah, and the reason is because I'm developing heuristics and schemas and algorithms. Algorithms are formulas to do things. And that's the same thing as I was trying, and my TA was sitting in my office watching me try to do some computer software stuff. And some of it I can do extremely well, but other times I just sit and stare at the computer going, I don't understand. I'm still trying. I don't have time to finish it, but I'll try. But as soon as you understand the algorithms and the heuristics and the schemas, what happens to your behavior? It becomes automized. This is a problem because in our class, we can't use those algorithms, all those things, because when you're doing an experiment, you have to get rid of all those algorithms. What is an exemplar? I forgot to define that one. The exemplar is your average of your observations. It's the most ideal of your observations. Like this, aside from being attached to a bunch of other things in here, okay? Because I fish, I'm really good at getting knots out. This is pretty much an exemplar yo-yo. Why is this pretty much an exemplar yo-yo? It's a basic yo-yo. It's about as simple as a yo-yo gets. Okay, it's made out of wood. It's from the 1950s. It's got a white string on it. It yo's and goes up and down, and it's a yo-yo. It's your basic exemplar. So if I showed this to anybody, would they recognize it as a yo-yo? Yes, and so that's what our averages are. The average are the most common observations. So you can start to see that why do we need all these statistics? What are these statistics doing? What is science doing? Think about what science does in general. Wait, what? Provides evidence because we automatically average things. If you are automatically average things, your experience is biased. Doing this racial equity thing that we're doing in class right now is actually really fun because I've been teaching this for a long time. But most people that are of the dominant race, good morning, we'll take a break in just a minute. Okay, so when people of the dominant race, whatever the highest race is, say there's no problem with race, I don't see race. How come people that are the dominant race don't ever see race? Well, we do, but we get offended when we're discriminated against. It's not the norm. And it's interesting to see how in sociology they talk about different lenses. Everybody taking soc right now? Yeah, lenses. Lots of lenses. Because it's really strange when you put yourself into someone else's situation and look at the world from their situation as opposed to your situation. Why don't we look at the world from other people's situations? Unless you live in their situation, you can't experience their situation. The saying's been around for a million years, is walk a mile in someone's shoes before you judge them. Yeah. But what you have to do is if you want to learn about a culture, you have to go immerse yourself in the culture. And that's because what you do is you increase the number of observations. You increase your degrees of freedom. But if you only expose yourself to two cultures, what happens? You can understand those two cultures, but you get a big perspective. No, but why can't you expose yourself to 10 different cultures and spend lots of time there? There's not enough time to make all those observations. See how this works? So humans, by nature, humans are scientists. And that's why humans develop science. Animals don't use science. Yet. Crows are breaking it out. They're working on it. But crows will test things. Anybody watch the Velociraptor? Velociraptors are supposed to be really smart. They're like a crow. They're what evolved into crows, is what a lot of people think. And so whenever they're looking for the fence, they test a different spot every time. Science. Okay, so take a break, because a couple people have to go. Sorry, Anna. Oh.